Every clock tells a story. On Earth, we measure our lives in seconds, minutes, days, and years' revolutions and rotations written into the very rhythm of our planet. It all seems so simple, so constant. But what if I told you that our clocks are just one tiny part of a much grander, much older timekeeper? What if the universe itself is a clock, one that has been ticking away since the very first moment of creation? This cosmic clock isn't made of gears and springs. Its components are far more epic. The steady fading of radiation, the relentless motion of galaxies, and the predictable decay of ancient atoms. For billions of years, this celestial timepiece has kept perfect time, recording everything from the fiery afterglow of the Big Bang to the rhythmic pulses of dying stars. It's a clock that whispers its secrets through the faint glow of background radiation and the steady beat of pulsars scattered across the cosmos. And today, humanity has finally learned how to read it. When we look up at the night sky, we're not just seeing space, we're seeing time. Take this incredible image from the James Webb Space Telescope. Each point of light is a galaxy, and many of them are so distant that their light has traveled for billions of years to reach us. We are literally looking back into the past. This raises one of the most profound questions we can ask. When did it all begin? How old is everything? As we dive deeper, we might even start to wonder, what does time truly mean? Well, to answer this, we've had to become cosmic detectives. We look at the universe's expansion, for instance. We see galaxies rushing away from each other, like shrapnel from a cosmic explosion. By measuring their speed and distance, we can rewind the clock. We can trace everything back to a single, infinitesimally small, incredibly hot point, the Big Bang. Our best measurements tell us this moment happened approximately 13.8 billion years ago. That's the age of our universe. But how can we be so sure? We don't just rely on one method. Cross-reference our findings using other cosmic clocks. For example, we study the oldest stars. Some stars found in ancient clusters are like celestial fossils. By analyzing their light, we can determine their composition, and from that, their age. The oldest stars we've found are just over 13 billion years old. They formed very soon after the universe began, perfectly aligning with our Big Bang calculations. It's like finding a birth certificate written in starlight. Then, there's another, even more subtle clock, the cosmic microwave background, or CMB. This is the faint leftover heat from the Big Bang, an echo of creation that fills the entire universe. Think of it as the universe's baby picture. By studying the tiny temperature fluctuations in this ancient light, scientists can create incredibly detailed models of the early universe. And we can even find clocks closer to home. Here on Earth, radioactive dating allows us to measure the age of rocks and meteorites. Certain elements, like uranium, decay into other elements, like lead, at a perfectly predictable rate known as a half-life. By measuring the ratio of uranium to lead in the oldest rocks on Earth and in meteorites that have fallen from space, we've determined that our solar system, our planet, and everything on it formed around 4.5 billion years ago. From the ashes of the Big Bang to the steady ticking of neutron stars, from the half-lives of atoms to the lingering glow of creation's first light, we have pieced together the universe's most extraordinary clock. We've learned to listen to the heartbeat of the cosmos itself. Each measurement, each discovery adds another piece to this grand puzzle, telling the story of time from its very first second to this very moment. It's a story that connects us all to the stars, to the galaxies, and to the beginning of everything. Time began in an explosion, or at least, that's how we describe it. The Big Bang wasn't an explosion in some location. It was an explosion of space itself. Everything everywhere, expanding all at once. In the very first fraction of a second time, space, energy, and matter were born together. Before that moment, the word before loses all meaning. There was no clock to tick, no past to precede the present. Physicists call this moment T equals 0, the absolute 0 point of cosmic time. In the first 10 to the power of minus 43 seconds, the Planck-era physics as we know it completely breaks down. This was a realm of pure quantum chaos, where even gravity hadn't yet separated from the other fundamental forces. Only after this fleeting instant did time, as a measurable dimension, begin to flow in a way we can understand. As the universe cooled and expanded, new eras emerged. The Grand Unification Epoch, where forces were merged. The Inflationary Epoch, when space ballooned exponentially. And the Radiation-dominated era, where energy was king and light filled the void. Each of these eras marked a shift in how time itself mattered. But how do you even measure time in a newborn universe? There are no clocks, no spinning planets, no orbits-only expanding energy fields. This is where the idea of cosmic time comes in. Cosmic time is the universal standard, a clock that ticks uniformly for all observers who are just floating along with the expansion of the universe. It's not tied to a planet or a star. It's woven into the very fabric of space-time. Imagine you could hit a pause button on the entire universe for just a moment. At that frozen instant, every observer, everywhere, would agree on the exact same cosmic time. That's the basis for cosmology's timekeeping. Today, our best models tell us that this universal clock reads roughly 13.8 billion years since the Big Bang. But figuring that out required us to decode a series of incredible cosmic clues. To understand how we date the universe, we first had to find its natural clocks. Unlike the ones on our walls, cosmic clocks are built into the laws of physics. They tick at predictable rates based on universal constants. We primarily use three types of these cosmic chronometers. First, there are radiation clocks. These measure time through the cooling and redshifting of light, like the famous cosmic microwave background radiation. Then we have decay clocks, which tell time by looking at the half-lives of radioactive isotopes that were forged in the universe's early moments. And finally, there are motion clocks. These extract time from the dynamics of cosmic expansion, the steady spin of pulsars, and the predictable orbits of celestial bodies.
Ow.
Each of these clocks tells a piece of the same grand story. And remarkably, they all converge on the same truth. Our universe is ancient, vast, and it is still ticking. But to truly grasp cosmic time, we have to face a mind-bending truth. Time is not absolute. Time actually stretches and compresses depending on gravity and speed. A clock on a mountaintop ticks ever so slightly faster than one at sea level. A single second near a black hole could feel like years to someone far away. This means that when we say the universe is 13.8 billion years old, it's not just a single number. It's a measurement made from our specific cosmic vantage point, a snapshot taken from our frame of reference. It's our local measurement of a universal phenomenon. So why does time seem to flow in only one direction? Physicists talk about the arrow of time, which is driven by a concept called entropy. Entropy is basically the universe's tendency to move from a state of order to disorder. The Big Bang was the ultimate moment of low entropy, perfectly smooth, ordered beginning. From that starting point, complexity and disorder began to grow. Every star that ignites, every atom that decays, is another tick of that arrow, pushing the cosmic clock forward. Without this increase in entropy, time would have no direction. Past and future would be indistinguishable. Once the universe began expanding, scientists could start piecing together a timeline using things they could actually see. The first light we can detect, the cosmic microwave background, emerged about 380,000 years after the Big Bang. The very first stars began to ignite around 200 million years later. Slowly, galaxies assembled, clusters formed, and the vast web-like structure of the cosmos took shape. These milestones created a cosmic chronology. But for a long time, we didn't know how to translate these events into actual years. It was until the 20th century that we finally built the tools to read this grand cosmic clock. The major breakthrough came in 1929. The astronomer Edwin Hubble made a revolutionary discovery. Almost all galaxies are moving away from us. And the farther away a galaxy is, the faster it appears to be receding. This was the first concrete evidence that the universe is expanding. If it's expanding, you can use that expansion rate as a kind of cosmic timescale. By measuring how fast space is stretching, a value we call the Hubble constant, scientists could essentially rewind the clock to estimate how long it has been expanding. Early estimates were all over the place, from 2 billion to 20 billion years. But over the next century, with better telescopes and more precise observations, we've narrowed that number down to the 13.8 billion years we know today. When cosmologists talk about the universe, They don't think of time as some external force. They see it as part of the geometry of space-time itself. Mass and energy actually warp space-time, and that curvature dictates how time flows. In dense regions, like near a galaxy, time slows down. In the vast empty voids of space, it speeds up. This means the universe doesn't age evenly everywhere. Different galaxies, star systems, and clusters all experience time slightly differently, depending on their local gravity. So when we say the universe is 13.8 billion years old, what we really mean is that's the time that has passed for a neutral, cosmic observer. One who is just floating along with the expansion, far away from any major gravitational fields. It's the most universal clock we can possibly imagine. From the instant it began, the universe has been ticking. Every atom, every beam of light, every expanding filament of the cosmic web carries a time stamp written in the language of physics. To read the age of the cosmos, we had to learn how to decode those imprints, the radiation that cooled, the elements that decayed, and the stars that spun like galactic metronomes. And that incredible journey of discovery begins by looking at the universe's most ancient light, the cosmic microwave background. Every civilization builds clocks to keep order against the chaos of change. But the universe built its own long before life or consciousness ever emerged. Its timekeepers are ancient, unerring, and written into the very laws of nature. These cosmic clocks tell us how long the universe has been unfolding. And they come in many forms, from radiation cooling through the void to atoms decaying deep inside ancient stars, to neutron stars spinning faster than a kitchen blender. Each one measures time differently. Yet they all point to the same astonishing truth. The universe has been ticking for roughly 13.8 billion years. So today, let's explore these incredible cosmic timepieces, the instruments that measure eternity. The oldest clock we can possibly read is light itself, the faint microwave radiation that fills all of space. Roughly 380,000 years after the Big Bang, the universe finally cooled enough for atoms to form. Before this, matter and radiation were locked together in a blinding hot plasma, a fog that scattered light endlessly. When the universe cooled to about 3,000 Kelvin, electrons and protons combined to form neutral hydrogen, and for the first time, light was free to travel. That light has been streaming through the cosmos ever since, stretched by the universe's expansion, until it now glows faintly in the microwave range. We call it the cosmic microwave background, or CMB, the oldest light we can see, the fossil radiation of creation itself. The CMB is astonishingly uniform. Temperature is about 2.725 Kelvin, just a whisper above absolute zero. But it contains tiny ripples, minuscule variations in density, from which all cosmic structure galaxies, stars, planets, us eventually grew. By measuring those ripples with incredible precision, using missions like COBE, WMAP, and Planck, scientists have reconstructed the entire early timeline of the cosmos. Those patterns encode everything: the universe's composition, its mix of dark matter, dark energy, and normal matter, its geometry, which we now know is flat, and most importantly, its age. From the CMB's data, cosmologists determined that the universe began 13.799 billion years ago. With a tiny margin of error, this ancient light, stretching endlessly through the void, is the first tick of the cosmic clock, the record of when time itself became visible. While the CMB gives us the universe's birth certificate, radioactive isotopes tell us about its middle chapters. Inside ancient stars and the explosive death of supernova, heavy elements like uranium, thorium, and potassium are forged. These atoms decay at fixed measurable rates, with half-lives that can span billions of years. By measuring the proportions of parent and daughter isotopes in very old materials, scientists can calculate how much time has passed since they were created. This method, known as nucleocosmicrography, is like carbon dating, but for the galaxy itself. Uranium-238, for instance, has a half-life of 4.47 billion years. Thorium-232 lasts even longer, about 14 billion years. By measuring these isotopes in ancient metal-poor stars, astronomers can estimate their ages with remarkable accuracy. Some of these stars, like HD 140283, nicknamed the Methuselah star, are nearly as old as the universe itself, clocking in at around 14 billion years old. Their existence confirms that the universe must have begun just before they did, perfectly validating the results from the CMB. These atoms, forged in stellar explosions and ticking away for eons, are the universe's slowest clocks, whispering the age of creation from deep within the elements themselves. When massive stars die, they sometimes collapse into neutron stars' ultra-dense remnants, where a single teaspoon of matter would weigh 1 billion tons on Earth. Many of these neutron stars spin incredibly fast, beaming out radiation along their magnetic poles. If those beams happen to sweep across Earth, we detect them as rhythmic pulses of radio waves. And that's how they get their name, pulsars. The pulsars are among the most precise natural clocks in the entire universe. Some spin hundreds of times every second, and their rotation rates are stable to within a few parts in a trillion, rivaling even our best atomic clocks here on Earth. By monitoring their pulses, astronomers can measure tiny distortions in space-time itself and even detect the faint ripples of gravitational waves crossing the cosmos. But pulsars also serve as cosmic chronometers. Over millions of years, they gradually slow down as they lose rotational energy. By measuring their current spin and their rate of slowdown, scientists can estimate their ages, tracing them back to the moment they were born from a supernova. Pulsars perfectly bridge the gap between stellar time and cosmic time, reminding us that even dying stars continue to keep time, their rotations fading like the ticking of an ancient watch. Beyond atoms and stars, the most profound measure of cosmic time comes from motion itself, from the expansion of space. When Edwin Hubble discovered in 1929 that distant galaxies are all receding from us, he revealed that the very fabric of the universe is stretching. The rate of that stretching, known as the Hubble constant, is the key to understanding how long the universe has been expanding. If you imagine running this expansion in reverse, like a movie played backward, all the galaxies would converge to a single point in the distant past, the Big Bang. By dividing the present-day distance between galaxies by their recession speed, we can get a rough Hubble age, the time since that expansion began. Modern measurements of the Hubble constant come from multiple sources. We use Cepheid variable stars and Type Ia supernova as standard candles to measure cosmic distances. We use data from the cosmic microwave background to infer the expansion rate from the physics of the early universe. We even cross-check those results with gravitational lensing and other methods. While there are still some slight discrepancies between local and cosmic measurements, a puzzle known as the Hubble tension, all of these methods converge on a similar age, about 13.8 billion years. This grand, dynamic motion galaxies flying apart in an expanding fabric of space-time is the universe's largest scale clock. Every second that passes adds another tick to the cosmic timeline. Orbiting the halos of galaxies are ancient relics of a forgotten era, globular clusters. These are tightly packed, spherical collections of hundreds of thousands of stars, all born at roughly the same time. They contain some of the oldest known stars in the universe, formed when the cosmos was still young and dark matter was just beginning to pull matter together. By modeling their stellar populations, looking at how bright and what color their stars are, astronomers can estimate their ages using the principles of stellar evolution. The results are incredible. Most globular clusters are between 12 and 13 billion years old, making them nearly as ancient as the universe itself. This provides a crucial lower limit for the age of the cosmos. The universe must be older than its oldest stars. These clusters are like celestial museums, preserving the chemistry and dynamics of an early universe, ticking silently through epochs longer than the age of our own Milky Way galaxy. The most distant galaxies ever observed by the James Webb Space Telescope formed less than 400 million years after the Big Bang. Their light has been traveling toward us for nearly the entire history of the universe. When we observe them, we aren't just looking across space. We're looking back in time, literally seeing the universe as it was when it was only 3% of its current age. The redshift of their light tells us exactly how much the universe has expanded since that light first began its journey. Every single photon carries a timestamp, its wavelength stretched in direct proportion to the growth of the cosmos. By assembling these distant snapshots, galaxy by galaxy, astronomers have built a timeline stretching from the cosmic dawn all the way to today. This look-back time is one of the most direct ways we measure the universe's age, linking the expansion of space directly to the flow of time itself. So we have all these different clocks: radioactive decay, pulsar rotation, the CMB's temperature, galactic redshift, and stellar aging. Each one measures time in a completely different way, on vastly different scales. Yet they all converge on a shared beginning, roughly 13.8 billion years ago. This isn't a coincidence. It's a profound confirmation. It shows us that the universe's physical laws are consistent, from the tiniest atomic nuclei to the largest clusters of galaxies. The same mathematics describes both the ticking of atoms and the stretching of space-time. This beautiful harmony tells us that time across the entire universe is connected by the same fundamental constants. By reading the CMB's afterglow, counting the decay of uranium atoms, timing the spin of neutron stars, and tracing the flight of galaxies, we have built not just one, but a whole constellation of clocks, each one pointing toward the same cosmic truth. All of our clocks here on Earth, from simple sundials to hyper-accurate atomic oscillators, are just local echoes of this much grander rhythm. The universe itself keeps time through its laws. And every photon, every element, and every orbit is a record of that eternal beat. But as perfect as these clocks seem, they raise a deeper question. Does time always tick at the same rate everywhere? Or could the universe itself experience time differently in other places under other conditions? That's a story for another time. Time feels universal. We live by it, measure it, and rely on it to make sense of change. But in the grand scheme of the universe, time is anything but simple. Behind every cosmic clock lies a mystery. Is time truly constant? Could the universe tick differently elsewhere? Or even stop ticking entirely? Today we're exploring the frontiers of cosmic time, where relativity bends it, gravity distorts it, and the quantum world may dissolve it altogether. In the early 20th century, Albert Einstein changed our understanding of time forever. Before him, time was thought to flow uniformly the same for everyone, everywhere. Einstein shattered that certainty. In his theory of relativity, time is a dimension interwoven with space, forming a four-dimensional fabric known as space-time. This fabric is elastic. It stretches and compresses depending on motion and gravity. If you move faster, your time slows down relative to others. If you stand in a strong gravitational field, your time also slows. This isn't just speculation, it's been measured directly. Atomic clocks flown on airplanes tick more slowly than identical ones left on the ground. Satellites in orbit actually experience time slightly faster due to weaker gravity, a correction that must be applied constantly for your GPS to work correctly. So what does this mean for the universe? It means there is no single now. Every observer has their own slice of space-time, their own present moment, their own clock that ticks differently. In regions of extreme gravity, near black holes or neutron stars, time's flow can slow almost to a standstill. To an outside observer, an object falling into a black hole seems to freeze at the event horizon. To the falling object itself, time continues normally, right up to its end. The universe's clock has many faces, all synchronized by the same laws, but running at different speeds. If the universe expands unevenly, or its structure grows more complex, could time itself stretch at different rates in different regions? This is a question at the forefront of modern cosmology. Some researchers propose that the universe's patchiness, the vast voids and dense clusters of galaxies, could slightly alter how cosmic time flows. In underdense regions, cosmic voids, space expands faster and clocks may tick slightly quicker than in dense regions bound by gravity. The effect is extremely subtle, but on smaller scales, this kind of time dilation is real. Astronomers have observed it directly in supernova explosions and quasars. Their light curves stretch precisely as predicted by relativity, because their light has to cross billions of light-years of expanding space-time. To observe the cosmos is to look across a distorted tapestry of time. But what happens when we go from the cosmic to the quantum? In relativity, time is a geometric dimension. But in quantum mechanics, it's something stranger. Quantum theory describes how particles behave, but it treats time as a fixed external background. That's a huge problem, because we know from relativity that time is asterisk, not asterisk fixed. When physicists try to merge these two great theories, time becomes incredibly slippery. At the smallest scales, near the Planck time that SA 10 to the minus 43 of a second, after the Big Bang, the very concept of time may dissolve. Some models, like loop quantum gravity, propose that space-time is granular, built from discrete atoms of geometry. In that world, there is no continuous flow, only jumps from one quantum state to another. In this view, the universe simply asterisk is asterisk a static configuration, containing all possible moments. And time is just our perception of moving through them. One of the deepest mysteries isn't just that time exists, but that it flows in only one direction. The laws of physics at their core work just as well forwards or backwards, but our universe is not symmetric. We remember the past, not the future. We see stars burn out, not reignite. Why? The answer lies in entropy, the measure of disorder. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time. This increase defines the arrow of time, the reason eggs break but never unbreak. The Big Bang, paradoxically, was a state of incredibly low entropy, smooth, ordered, and simple. As the universe expanded, gravity and chaos increased entropy, giving rise to all the complex structures we see today. So the arrow of time points away from the Big Bang, from order toward disorder. But why was the universe's entropy so low to begin with? That remains one of the greatest unanswered questions in all of science. If time can stretch, bend, and even dissolve, could it ever reverse? In theory, certain solutions to Einstein's equations allow for closed time-like curves, paths through space-time that loop back on themselves, making time travel mathematically possible. However, most physicists believe nature prevents such paradoxes. Stephen Hawking even proposed a chronology protection conjecture, suggesting that quantum effects would destroy these loops before they could form. Still, in some cosmological models, particularly those involving a multiverse, time might behave differently in other domains. There could be universes where entropy flows in the opposite direction, or where time doesn't exist at all. Closer to home, near black holes, the distinction between future and space can blur entirely. This relativity of experience reminds us that the universe's true age depends not only on physics, but on where you're watching from. Even if time began with the Big Bang, will it ever end? Our universe is expanding and accelerating, driven by dark energy. If this continues in trillions of years, distant galaxies will disappear beyond our observable horizon. Stars will die, black holes will evaporate, and matter itself may decay. Eventually, only a cold, dark void will remain. This is the heat death of the universe's state where entropy is maximized and nothing ever happens again. In that state, time loses all meaning. Without change, the arrow of time ceases to exist. The cosmic clock would stop ticking. But not all models agree. Some suggest the universe could one day reverse its expansion and collapse in a big crunch, resetting the cosmic clock. Others imagine an endless cycle of expansion, contraction, and rebirth. In these models, time never truly ends. It just transforms. After a century of revolutionary physics, one mystery remains untouched by equations. What asterisk is asterisk time itself? We can measure it with atomic precision, can stretch it, slow it, and even freeze it in theory. But we still don't know what it is. Is it a dimension? An illusion? A property of quantum information? Whatever the answer, time is the medium of our existence. It began with the Big Bang. It will end or transform when the cosmos reaches its final stillness. And though we've measured its passage across billions of years, its true nature remains the universe's greatest enigma. The cosmic clock may tell us how old the universe is, but not why it ticks at all. For billions of years, the universe has kept time in silence, measured in the expansion of galaxies and the decay of atoms. But only one species has ever tried to count it. From the shadows of ancient temples to the lasers of modern observatories, humanity's history is a struggle to understand time, to grasp the rhythms of the cosmos and bring them under our control. In learning to measure our minutes and hours, we eventually learned to measure the age of the stars themselves. Long before the first calendars, humans watched the sky. The earliest civilizations noticed the sun's rise and fall, the moon's phases, and the steady migration of stars. These patterns gave birth to our first clocks: natural, celestial, and cyclical. The day came from Earth's rotation, the month from the moon's orbit, the year from our revolution around the sun. The sky was humanity's first calendar, and it gave order to life: planting, harvesting, celebration, and rest. Ancient monuments like Stonehenge, Machu Picchu, and Nabda Playa weren't just temples, they were instruments for tracking celestial time. Timekeeping was sacred. It aligned humanity with the heavens. In Egypt, the flooding of the Nile was predicted by the rising of Sirius, the brightest star. For early humans, to know time was to know nature's will and, perhaps, to touch eternity. As societies grew, so did the need for precision. Celestial cycles were no longer enough. We wanted to divide the day to own time itself. In the Middle Ages, mechanical clocks appeared, first in monasteries, later in cities. These early machines transformed time from a cosmic rhythm into a measurable commodity. For the first time, time could be controlled. By the 17th century, Galileo and Huygens introduced pendulum clocks, improving accuracy to mere seconds per day. With that precision came a revolution in navigation. Longitude, the key to global exploration, depended on knowing the exact time difference between two locations. In 1759, John Harrison built the first marine chronometer, a clock accurate enough to find position at sea. With it, human exploration extended across the planet, guided by the ticking of mechanical stars. We had begun to master time on Earth, unaware that the universe's clock was ticking on a much grander scale. Until the 18th century, most believed the world was only a few thousand years old. Time was measured in human generations, not cosmic epochs. That all changed when natural philosophers began studying the Earth itself. James Hutton, in the late 1700s, looked at eroded cliffs and fossilized strata and saw evidence of an unimaginably ancient world. He wrote, "We find no vestige of a beginning, no prospect of an end." This was the birth of deep time, the realization that Earth's history spans billions of years, long before humanity ever appeared. The discovery of radioactivity in the 20th century turned this insight into measurement. By studying uranium decay in rocks, scientists could determine their ages with precision. Earth, it turned out, was about 4.54 billion years old, a revelation that reshaped humanity's place in the cosmos. For the first time, we understood that time's domain wasn't just human, it was planetary, cosmic, eternal. As our curiosity deepened, our clocks evolved. Pendulums gave way to quartz oscillators, and quartz 2 atomic clocks instruments so precise they lose less than a second in billions of years. The atomic clock doesn't rely on gravity or mechanics. It measures time through the vibrations of atoms themselves. The most accurate clocks today, based on ytterbium or strontium, can measure time so precisely that they detect the difference in gravity between your head and your feet. These clocks revealed that Einstein was right. Time does flow differently depending on where you are. Even on Earth, time runs slightly faster in orbit than on the ground. Difference GPS satellites must constantly correct for. Our machines had become so sensitive, they could now feel relativity itself. And in doing so, we joined the cosmic conversation, reading time as the universe writes it. Humanity's greatest triumph was to extend timekeeping beyond Earth, to build clocks that read the age of the cosmos itself. By comparing stellar brightness, atomic decay, and galactic motion, astronomers constructed a cosmic chronology. The universe's birth, 13.8 billion years ago. The first stars around 200 million years later. The formation of galaxies, planets, and life fall nested within this temporal architecture. Every telescope, every spectrometer, every detector is, in essence, a timepiece. Measuring the intervals between cosmic events, astronomy is timekeeping on a universal scale. When we observe a distant galaxy, we see light that left billions of years ago. Our telescopes aren't just looking across space, they're looking back in time. And when we measure the redshift of that light, we're reading the expansion of the universe, the ticking of space-time itself. Every discovery in cosmology is at its core a reading of the cosmic clock. For all our scientific precision, our experience of time remains deeply human. We feel its flow through memory, anticipation, and decay. Time is both our measure of life and the boundary of it. Unlike stars or galaxies, we are conscious of time's passage, can reflect on the past, and imagine the future a gift, but also a burden. From this awareness springs our obsession with recording, predicting, and sometimes escaping time. Our calendars, our art, our philosophy are attempts to make peace with the relentless ticking of existence. We live within time, but we also shape it, dividing it into seconds, lifetimes, and histories. And by extending our gaze to the cosmos, we've learned that our personal hours are fragments of a vast 13.8 billion year continuum. The clock that governs our days is the same one that governs galaxies. Today, every atomic clock on Earth is synchronized through the international system of TMI Global Web that defines the second based on atomic vibrations. It's no poetic coincidence that those same vibrations are governed by the same physical constants that shaped the early universe. When we measure time, we participate in the cosmic order itself. Our seconds, our years, our centuries are calibrated to the heartbeat of the universe. We have gone from tracking the rising sun to reading the microwave background, from counting seasons to calculating cosmic epochs, from marking our lives to mapping the life of the universe. Every clock we've ever built, sundials, pendulums, atomic oscillators, is a reflection of the same ancient truth. The cosmos keeps time, and we have finally learned to listen. Our mastery of time has made modern life possible. GPS navigation, global communication, stock markets, spaceflight. Every digital system relies on synchronized time down to the nanosecond. But this also reveals our dependence. If the cosmic clock were to falter, if atomic constants shifted, or cosmic expansion change, their entire technological civilization would lose its rhythm. It's a humbling reminder. Even our most precise clocks, our local instruments, synchronized to a universe we do not fully understand. We build systems to measure time, yet the deeper we look, the less we seem to grasp what time truly is. In the end, humanity's obsession with time is an echo of the universe's own heartbeat. We measure time to find meaning, to locate ourselves within the grand unfolding. Every calendar, every clock, every time stamp on a photograph is a confession. We fear time, but we also love it. We fear its brevity, and yet it's the very thing that makes life precious. We chase its precision because we know it's unstoppable. And when we look up at the stars, we see time itself shining back at us from long ago, crossing the darkness to remind us that nothing lasts forever, yet nothing truly vanishes. From stone shadows to atomic vibrations, humanity has tried to synchronize with the universe's pulse. And though we have measured the age of galaxies, the universe's true clock is still running, steady, silent, infinite. We can count the beats, we can trace the seconds, but we cannot yet escape the mystery of the rhythm itself. Every clock tells a story. From the sundial to the atomic clock, we've measured our lives in fleeting ticks. For thousands of years, humanity looked up and wondered, when did it all begin? Was the cosmos eternal, or was there a moment of creation? The answer wouldn't come from myth, but from light, ancient light, whispering across billions of years. This is the story of how we learned to read that light and discovered the age of everything. For most of history, the universe was believed to be timeless, static, eternal, and unchanging. Even Isaac Newton, whose laws of motion described the planets with unmatched precision, saw time as an infinite river. In his view, the cosmos was the clock, vast, mechanical, and eternal. That idea held for centuries, till the 20th century shattered it. In 1915, Albert Einstein published his theory of general relativity, describing gravity not as a force, but as the curvature of space-time itself. Space and time were no longer separate. They were intertwined, dynamic, and malleable. His equations allowed for a universe that could expand or contract, but he didn't like that. To keep the cosmos static, he added a cosmological constant, a mathematical patch to hold the universe still. He would later call it his greatest blunder, because just a decade later, a humble astronomer from Belgium would prove the universe was anything but still. In 1927, Georges Lemaître, a Catholic priest and physicist, proposed something radical. If galaxies are moving away from each other, then the universe must have been smaller in the past. Perhaps it all began from a primeval atom, a single point of creation. Few took him seriously, till 2 years later, Edwin Hubble, working at the Mount Wilson Observatory, made an astonishing discovery. Studying the light of distant galaxies, Hubble noticed their light was redshifted, stretched toward longer wavelengths. That redshift meant one thing: motion. Everywhere he looked, galaxies were racing away from us. And the farther they were, the faster they moved. This became known as the Hubble law for the first time. Humanity had a way to measure the age of the universe by running the cosmic expansion backward, like rewinding a film. The principle was revolutionary. The universe had a beginning. If the universe began with a hot, dense explosion, what we now call the Big Bang, then its glow should still be faintly visible today, stretched and cooled by billions of years of expansion. A cosmic afterglow. In 1965, by complete accident, 2 radio engineers at Bell Labs, Arno Penzias and Robert Wilson, discovered a mysterious noise in their antenna. It came from every direction and never went away. At first they thought it was interference, maybe even pigeon droppings. But it wasn't noise. It was the cosmic microwave background, or CMB, the oldest light in the universe. Released 380,000 years after the Big Bang, that faint microwave signal became the universe's most ancient timestamp. Its temperature and tiny fluctuations carried encoded information about the universe's age, density, and fate. The CMB became the ultimate cosmic chronometer. While astronomers looked outward, physicists looked inward. The discovery of radioactivity opened up a new kind of clock, one that ticks in the heart of atoms. Every radioactive isotope decays at a constant rate, its half-life. By measuring how much of an isotope remains, scientists can determine the age of almost anything. Using isotopes like uranium and potassium, geologists dated Earth's oldest rock sand meteorites from the birth of our solar system to about 4.5 billion years. Later, by studying ancient stardust, they could trace when the first elements were forged in stars. This atomic clock, ticking on a microscopic scale, complemented Hubble's cosmic clock, both pointing to a universe that was billions of years old. But there was a problem. Hubble's original estimate for the expansion rate suggested a universe just 2 billion years old. Earth was already known to be older than that. Something was wrong. Over the decades, astronomers refined the value of the Hubble constant using more accurate standard candles, like keyfied variable stars, whose pulses reveal their true brightness, and type A supernova, stellar explosions of consistent luminosity. Each new generation of telescopes, from Mount Wilson to the Hubble Space Telescope, and now the JWST, improved our measurements. Today, multiple methods converge on a value that places the universe's age at around 13.8 billion years. The clock, once crude, now beats with cosmic precision. Modern cosmology doesn't rely on just one method. It uses many interlocking clocks. The cooling rates of dead stars, called white dwarfs, act as stellar timepieces. Life cycles of stars and ancient globular clusters trace the early epochs of galactic formation. And pulsars, rotating neutron stars, act as extraordinarily precise cosmic clocks. Each method is independent, yet they all tell the same story. Strengthening our confidence in the universe as age, a cross-checked web of timekeeping that spans from atoms to galaxies. The era of precision cosmology began in the 1990s. NASA's COBE satellite mapped the cosmic microwave background, confirming its near-perfect uniformity and the tiny fluctuations that seeded galaxies. Then came WMAP in 2001, providing sharper data that pinned the universe's age at 13.77 billion years. And in 2013, the Planck mission refined it further to 13.80 billion years, an astonishing level of precision. Planck's data also revealed what the universe is made of: about 5% normal matter, 27% dark matter, and 68% dark energy. Each component affects the universe's expansion, and thus, its timeline. We had built machines capable of reading the afterglow of creation itself. This journey also redefined what we mean by time. Is time a dimension or an emergent property? Does it flow or just appear to? Einstein's relativity taught us that time depends on the observer. Quantum mechanics suggests it may not even be fundamental. So every cosmic clock we build isn't just a tool for measurement, but a mirror reflecting our own limitations and understanding what age truly means. Today, when we say the universe is 13.8 billion years old, it's not a guess. It is the culmination of centuries of ingenuity of mathematics, observation, and imagination. Every clock, from radioactive decay to pulsar spin, tells the same story. Time began. The universe has evolved, and we exist midway through its unfolding. We are the universe's timekeepers, small minds reading vast epochs, turning starlight into history. The search for the universe's age was not just a scientific journey, it was a human one, a quest to find our place in the story of everything. And what we've discovered is that time, vast and ancient, has led precisely to now. We have measured time, counted its ticks, and traced the universe's age across 13.8 billion years. But what about the future? Does time stretch on forever, or will it one day falter, twist, or cease altogether? To answer that, we must peer into the far future beyond the lifespan of stars, galaxies, even atoms, and into the ultimate fate of the cosmos. In 1998, two teams of astronomers made a shocking discovery. The expansion of the universe is accelerating. They observed distant type Ia supernovae, the universe's standard candles, and realized that galaxies are moving away faster than expected. This acceleration is driven by a mysterious phenomenon known as dark energy, a force that counteracts gravity across cosmic scales. If this continues indefinitely, galaxies beyond our local group will eventually recede from us faster than the speed of light. They will vanish beyond our observable horizon, leaving the Milky Way isolated in an ever-darkening void. The cosmic background light will fade, and the universe will grow colder, emptier, and quieter. The cosmic clock will keep ticking, but its heartbeat will become almost imperceptible. Physicists call the ultimate fate of a universe dominated by this expansion the heat death. It's a future governed by entropy, the relentless increase of disorder. As stars burn out and matter decays, all energy will spread out evenly. Without differences in temperature or energy, nothing can happen. No work can be done, no change can occur. And without change, how can time have any meaning? Even if an advanced civilization could survive for trillions of years, the universe itself would become a silent, static, and unchanging place. Time, in any practical sense, would cease to be relevant. We are not just witnessing the universe's birth, but also the slow, inevitable march toward its ultimate stillness. In this desolate future, black holes will be the final timekeepers. Their immense gravitational grip warps time so severely that near their event horizons, seconds for a falling object could stretch into millennia for distant observers. But even these cosmic titans are not eternal. Over unimaginable timescales, Stephen Hawking predicted that black holes will slowly evaporate through a process now called Hawking radiation. As they radiate away their mass, they will shrink and finally disappear in a final flash of light. When the last black hole is gone, the universe will contain only a diffuse soup of particles and low-energy radiation. At this point, all classical, clocks atomic, stellar, galactic will be gone. The universe's ultimate expiration will render time a meaningless concept. But what if our understanding of time is incomplete? Beyond classical physics lies the quantum frontier, where the very fabric of reality behaves in strange ways. Some theories of quantum gravity propose that space-time isn't smooth, but granular, composed of discrete atoms of space and time. Other theories suggest time isn't fundamental at all, but an emergent property, a pattern arising from the complex quantum correlations between particles. In such scenarios, the end of the universe might not be a simple freeze, but a profound transformation. The concepts of before and after could dissolve entirely. Time could merge with space or collapse into a timeless quantum state. If so, the cosmic clock isn't just stopping, it's becoming something else entirely, something we can't yet comprehend. Not all theories, however, predict a definitive end. Some models of cyclic cosmology suggest the universe may undergo repeated cycles of expansion, contraction, and rebirth. The Big Bang might have been just the latest in a potentially infinite series of beginnings. In this view, our universe could one day stop expanding, reverse course, and collapse back into a superhot, superdense state, triggering a new Big Bang, a big bounce. In this cosmic reboot, time doesn't truly end. It transforms, flowing differently in each new universe. The clocks of one cosmos may vanish, but the fundamental rhythm of existence could persist forever, in a pattern far beyond our current ability to observe. While cosmic time stretches across billions and trillions of years, our lives unfold in seconds, minutes, and years. The contrast is profound. We experience time as a linear, forward-moving river, yet the universe treats it as a vast, malleable dimension. Our calendars, clocks, and memories are the tools we've created to navigate the cosmos on a human scale, brief fleeting beats against the eternal pulse of the universe. Knowing the universe's ultimate fate may seem abstract, but it frames a deeper truth about our own existence. Time is finite for us as individuals, yet it feels infinite in the larger cosmic context, rhythm we can glimpse but perhaps never fully grasp. Even as we measure cosmic time with incredible precision, its true essence remains a profound mystery. What is asterisk time? Is it a fundamental dimension of reality, or an emergent illusion? Can it truly end, or will it persist in ways we cannot yet imagine? Our cosmic clocks, from pulsating stars to the fading glow of the Big Bang, tell us how long the universe has existed, but they don't answer why time exists, or what its ultimate nature might be. We have learned to read the face of the cosmic clock, but we are still a long way from understanding how it was built. Time is the thread that weaves the entire cosmos together. From the first photons escaping the primordial plasma to the last black holes evaporating into darkness, the universe tells its story in ticks, pulses, and vibrations. Our lives are fleeting, our entire history, just a momentary flicker. Yet we have somehow learned to measure the rhythm of existence itself. The cosmic clock keeps ticking silent, relentless, and profound. As we gaze upward at the stars, we realize that understanding time is not just a scientific quest, it's a deeply human one. To read the age of the universe is to confront the nature of existence, mortality, and infinity. We are here now, measuring the cosmos. And in doing so, we join the universe's most enduring tradition, keeping time, listening to its heartbeat, and marveling at the infinite story it continues to tell. Thank you so much for joining me on this journey to the end of time. If you enjoyed this exploration of the cosmos, don't forget to like this video and subscribe to the channel for more deep dives into the mysteries of our universe.